summarize, HBase is a distributed storage software. It can form the basis of a cloud scale storage. Right, can you hear me now? Okay. So my slides talk mostly about HBase as an open source project. To start with, I have a lot of material on my slides, and I probably won't be able to cover it all in half an hour. I apologize for that. My slides will be available at hbase.org, along with the other information about our project, so feel free to visit there. Okay, so what is Bigtable and HBase? It's a response to challenges with storage and computational aspects of very large data sets, specifically scalability issues, and limitations with relational databases at very large scale. So Bigtable was developed at Google, but their solution is proprietary. So HBase is one of several open source projects which are more or less faithful Bigtable clones, making this infrastructure available in an open source manner for anyone to use. HBase also has a focus with the most recent release on real-time responsiveness, so fast, random access, and high write update rate. So it's an option to build a very large-scale structured storage platform, the features of which meet the requirements of many so-called Web 2.0 use cases. So a little bit more about the fundamentals of the problem. So when you think about databases at scale, the access to that data, if you're updating it, is dominated by the seek transfer rate of modern storage devices. And so this has come about because CPU RAM and disk size double about every 18 to 24 months, but the seek time has remained nearly constant, growing at about 5% over many years. So as you probably know, there are two database paradigms. There's the seek paradigm, which most relational databases use. Updates and accesses use B trees to seek around the disk, find a location where to store the data, and then store it. Another model, which is used by Bigtable and MapReduce, where when flat files are used, is a transfer model where rather than search and replace, the entire database is rewritten. And it actually turns out that at very large scale, it is more efficient to completely rewrite the database than it is to seek and replace. An example of which is here. Just suffice it to say, it's several orders of magnitude faster to completely rewrite the database for use cases such as this. So at scale, relational databases have performance problems, especially considering analytic workloads. Analytic workload is basically table scan. In which case, when you're dealing with very large data, it exceeds the ability of any single server, no matter how large the server is, to process all of that query in a timely manner. It also gets to be very expensive to use SON and other storage, network-attached storage devices. So Google's insight was, well, why don't we try to design something which operates simple and can operate on cheap hardware, and avoid some of the problems you see on the latter part of my slide, where in relational database systems, especially if you're using a highly normal schema with maybe foreign key references or secondary indexes or whatever, the weights and deadlocks rise non-linearly with the transaction size and concurrency. So especially if you're doing large updates or large scans, the performance impact on the database engine is large. And when you use open source relational databases like MySQL or Postgres, when you use those at scale for performance reasons, often you give up most relational features such as secondary indexes performance anyhow. So what if we traded relational features for performance? We remove relational features from the data model. We avoid weights and deadlocks by minimizing unnecessary locking. Provide a transparent and horizontal scalability without architectural limits, and provide fault tolerance and data availability by way of the same mechanisms, and also allow it to run on cheap commodity hardware. So this is Bigtable. Invented by Google, the way they describe it is it's a distributed storage system for managing structured data that is designed to scale to a very large size. Petabytes of data across thousands of commodity servers. Its data type is specifically a sparse, persistent, multidimensional map. The way I like to describe it, though, is a column-oriented, semi-structured data store, which is strongly consistent, and it's an engineering response to the storage of massive data sets, data analytic use cases, and the expense of commercial solutions for the same. In contrast to the earlier slide, which talked about the non-linear behavior of relational database engines at very large scale, Bigtable, in contrast, is logarithmic or linear for all of its operations, despite extreme scale. But to gain this performance advantage, you give up just about all of the relational model and its benefits. So HBase is an open source project, a Hadoop sub-project under the Apache Software Foundation umbrella. It was originally written at a company called PowerSet in 2007. PowerSet has been acquired by Microsoft and continues to get support from Microsoft, which we were grateful. They allow several of their employees to work on HBase full-time. And Trend Micro also allows a developer to work nearly full-time on HBase, which is myself. So HBase is a faithful clone of the proprietary Bigtable architecture, enhanced with additional features that have been developed by the community. For example, fast vault recovery by way of Zookeeper, which is also an Apache, Hadoop sub-project. We support query pushdown via server-side query and scanner filters. We have optimizations for real-time queries. Our data storage cluster handles rolling restarts and other various smaller enhancements. So let's talk a little bit more about what is Bigtable and HBase. It's not a SQL database. As I've already talked about, the data model does not support normalized schemas. So really, if you think of HBase in terms of database, it's you do have columns, rows, and tables, but you have only a primary index. And its engine is not a relational query engine. It's something totally different. It's basically a scan engine, a table scan engine, a self-scaling table scan engine. Unfortunately, I don't think we'll have time to go into more detail about this. And another limitation of Bigtable and HBase is that there's limited atomicity and transaction support. Really, you can take a lockup on a row, update a row, and that's it. So the data model of HBase is a map, basically a hash map, but the keys are multidimensional, right? You have your table, right, and then you have rows, and then columns within that row. Columns can optionally have a qualifier, and there's also a time dimension, timestamp, so we store data with timestamps as a first-class indexing option. You could think of it in some ways like a spreadsheet, an enormous spreadsheet. So keys are arbitrary strings. Access to row data is atomic. And an important feature of the Bigtable and HBase data model is the concepts of multi-versioning and timestamps. You store a data to a specific cell. You can have more than one version in that cell. It's indexed by time. So the canonical use case is a data storage for web crawls, where the web crawl happens periodically. And what this allows you to do in a very clean manner is to store data in such a way that snapshots of changing web content can be reconstructed over time. So HBase is column-oriented storage. It's a little bit like a spreadsheet, but you should think about instead in terms of tags. Right? Rows are index pointers to a series of tags. So within the row, you have a number of keys and values. Any number of keys and values, perhaps millions. So a table consists of one or more column families. Column families are scoped with the optional qualifier, which forms an additional level of indexing. And on disk in HDFS, the file system part of the Hadoop software stack. HDFS is the distributed file system. In that storage, each column family is stored as a file. keys which are similar to each other, right, are packed adjacent to each other into blocks. So it's a very efficient means of storage. The takeaway here is that in general it's fast and cheap to scan adjacent rows and columns. So rows are stored in sorted order. Each column has its own file. As tables grow, they are dynamically split into regions. Regions are then distributed to a number of servers called region servers. There can be any number of region servers on the platform. There's no architectural limit. In theory, you can support a very, very large amount of data, petabytes of data, by just adding more region servers over time to serve this data as these tables grow. So each table has a region split limit, and once the amount of data contained within that region reaches this threshold, the region is split in half. And another component of the HBase architecture, the master, ensures that regions are load balanced across the cluster. The master also handles redeployments if an individual node fails. Okay, so this is a bit more technical information that we probably need to discuss. So let me talk a little bit about HBase 0.20, the latest upcoming release. This is the first ever performance release of HBase. The focus for this release has been on improving performance for random access times, scan times, insert times. And so now we can say that as a random access store, HBase is well suited for the storing and serving of data for many types of web applications. For prior releases, 0.19, some of you may be familiar with, had good random access time sometimes, but unfortunately high latency and variability in other cases. Now that has changed. There are now significant performance gains due to the re-architecture for this release. Our random reties are similar to, say, MySQL. About 20 to 100 times faster than our previous releases, with far less variability than before. And in general, we achieve probably an order of magnitude better performance for most operations: scans, inserts, updates, deletes, what have you. So some specific performance numbers. Like I said, this data is available on hbase.org. So what did we do for this release? HBase is implemented in Java. And one can have a philosophical discussion on whether Java is the most appropriate language in runtime system to implement server-side software. Sometimes the garbage collector can trip you up, etc. And also the libraries supplied with Java, although algorithmically nice, have performance problems. So if you use these very elegant abstractions in the Java library, you run into performance issues. So we realized this, right? So our guiding philosophy for 0.20 was to essentially un-Javify everything. So we do a lot of the work ourselves now, internally. Such things as zero copy reads, block-based storage, no use of Java trees, that type of thing. A custom-developed heap sort. Really thinking more in terms of implementing HBase as if it was a C or C++ application, but in the Java language. And so so we have a new data format, a new file format, a new block caching subsystem, a new query API, a new result API, optimized serialization at all layers of the system, and a new way of doing scanning. So through this re-architecture, we improved our performance by an order of magnitude. We also integrated Zookeeper. During prior releases, we had this concept of master, right? And so I talked about it a little bit briefly, but although there are n number of region servers, any of which can fail and their regions will be reassigned and you don't lose any data availability, right? There is one master, which is a single point of failure. And this is actually a limitation, arguably, of the Bigtable model, right? So in order to be consistent in the way that Bigtable is architected, there needs to be a master, a control function. So when we take a step back from that a little bit, and so some of the master functions actually can be distributed, right? So we look at the Zookeeper subproject of Hadoop, which is a in-memory database designed to be fault tolerant when set up in a 2n+1 form. And we find that Zookeeper has a number of features built in which allow us to eliminate the master as a single point of failure in our architecture. So we now track cluster membership and detect dead servers via Zookeeper. We can do recovery of failed region servers much more quickly than before. We have hot standby masters, which can detect when the other master fails and take over seamlessly. This way of managing the master region server relationship allows for rolling upgrades of the cluster during upgrades for point releases. So there's no need to take down the service, the data storage service, to update for example, bug fixes. And some aspects of cluster configuration can be reconfigured because it's written into Zookeeper and not stored somewhere else without a full cluster restart. So perhaps this is, from my point of view as an HBase developer and architect, right, having no more single point of failure in HBase is the primary achievement of this release. Now we also have improved web service connectors, which implement RESTful semantics. So HBase can be used in a similar manner as the S3 service, right? And one new contribution to the HBase project, so-called Stargate codename, is something that I hope to develop going forward to actually serve as a way for enterprises to build S3-like storage, right, internally in their enterprise. So HBase also has some extensions. Earlier, I talked about how you give up most of the features of relational databases when you use Bigtable or HBase. But we do have transactional tables. They're slower. They're an add-on. It's not fully implemented. If a region server fails, for example, during a transaction, the recovery of this is not fully implemented. However, if there is no region server failure, then you can initiate a transaction which spans multiple regions, update a row, and then the transaction will either commit or abort, right? If there have been other changes, because the transactional table subsystem uses something called optimistic concurrency control, which basically says, optimistically, I assume that the transaction is going to complete, and so it will if there have been no other changes to that row. But if there have been, then it will roll back, and it's the client's responsibility to try again. Okay. We also support a secondary index capability. We can have any number of secondary indexes in addition to the single primary key that the Bigtable data model supports. And we achieve this by maintaining server-side a separate index table for each secondary index. And we use the transactional layer to maintain the consistency of these indexes. So the current status of HBase, we're in somewhere between release candidate 1 and release candidate 2. There are 3 open issues. Probably RC2 will be ready in about a week. HBase is in production use at several companies. PowerSet Stream we stumbled upon, and also in evaluation and development for production use at Trend Micro. We have lots of new users appearing now in the HBase users channel, mailing list, and on in our IRC channel. And they're having standard new user issues, so we still really need a good beginner how-to, but this is improving all the time. A little bit more about HBase at Trend Micro. So Trend Micro has this thing, the Smart Protection Network, right? And I won't describe what it is, but just suffice it to say that we have to look at a lot of threat data, and we have to make a lot of correlations and update our understanding of the threat landscape with the internet in real time. And this is a data-intensive activity. There are lots of data, massive amounts of it. So Trend Micro's intent is to use HBase as a storage platform for very large data sets and for archival storage, and use this platform to do correlation over massive data sets. And we've already used HBase with some success for threat research. A Trend Micro employee is an HBase committer, that's myself. And I'm happy to say that Trend Micro is open source friendly. But HBase needs your help. If you have a need for a very large scale data storage, if you have and you want to do it on commodity hardware in a way that is fault tolerant and highly available, then HBase might be for you. It's open source, it's in development, it's not perfect. So I would recommend you to try it out and discuss on our mailing lists or by IRC your results, right? At this point in our project's lifetime, we especially appreciate bug reports. And then, of course, help with bug fixing. Our developer community is about 10 core developers. We have another 10 or 20 strong contributors and then a larger user community. So certainly we could use help with bug fixing, help with performance improvements, and help with the development or new and improved features, especially if you find HBase meets approximately 90 or 95% of your requirements, and there's only that last 5 or 10% of functionality that you require to support your use case. We would encourage you, rather than develop something yourself, to look whether you can use HBase and just add this function. And we would respectfully ask that you consider contributing back any such enhancements to the community. We certainly welcome that. So a little bit more about our roadmap. I talked about how we distributed some of the master responsibilities from a single point of failure to a Zookeeper quorum. We would like to further distribute the master responsibilities and make the master as small as possible. In my vision, I would like to see actually it be there should be no master. There should be only region servers. They should cooperate to coordinate region assignment and failure recovery and such through distributed and emergent behaviors. We certainly won't get there for the next release, but maybe some more after. Like I said, HBase is implemented in Java, and our client side is also Java, so it requires some level of Java integration, although we do have a thrift gateway and a RESTful web API. These don't achieve the same performance, of course, as the native API. But we aim to change that by producing a language-agnostic binary RPC and a native C, C++ client library with performance that meets or exceeds the current Java option. Something that I plan on working on is replication for multiple data centers. HBase, like the Hadoop file system, if you're familiar with it, is something that can scale up very large, but it scales in cluster, right? It scales in LAN, not in WAN. So you can't have an HBase or an HDFS federation which spans data centers, right? The latencies and chance of network partition across the WAN links so negatively impact the performance of these systems that it's not feasible to try that kind of deployment. So what do you want to do if you want, for disaster recovery or business continuity purposes, have multiple geographical locations where your workflow operates, right? Well, so you need replication in this case. So we aim to do that. So cells, in addition to being associated with a row, a column, optional qualifier, and a timestamp, will also have a scope. Thank you. 5 minutes. Further optimizations on algorithms and data structures, a tool for repairing corruptions on disk, a option for returning. So if you have a column which has millions of data items in it, you need an RPC to retrieve that. It's large. Your client needs to have a large memory buffer to support that. If it doesn't, it will blow up. So what we like to do is avoid that necessity by allowing inter-row scanning, where you say if you have a row with a column which has millions of values, maybe you only want to retrieve 1,000 at a time, right? This is something we'll do. And currently, through much of the Hadoop stack, when HBase included, there's a lack of access control, strong security. So this is something for beyond 21 discretionary access control. So for more information, please consult these resources. And at this time, if there are any questions, please.
Yes, as far as I know, there are a lot of distributed key value storage on the internet, like Cassandra and Project Voldemort. This HBase in version 0.2 has better latency and response time than other frameworks. Thank you.
Yes. I would say that there are a number of key value stores, right? Bigtable is not really a key value store; it's more. It's not a flat key space; it's a multidimensional key space. So I don't consider Bigtable and key value stores equivalent. But in the space of Bigtable-like storage systems, there is, to my knowledge, Hypertable, Cassandra, and HBase. And I know as for Trend Micro, we looked at all three. So I would say that Hypertable is faster, but not as stable. And with the latest release, one internal benchmark we had was we needed to be at least as fast as Hypertable. And I think that we've achieved that. Cassandra is kind of a different beast. Cassandra is kind of like a HBase, but put on top of Amazon's Dynamo. Have you heard of Amazon's Dynamo? Yeah. So it's like that. It's a really interesting hybrid. It's peer-to-peer Bigtable, and our architecture is not like that at all. It's the traditional, or I guess traditional is the word to use, Bigtable architecture. It's kind of an apples and oranges comparison to compare those as well. I think that we perform on par with Cassandra, just in terms of performance. Their write path is more available than ours. They've specifically engineered their system such that their system will always accept writes, right? And no matter what. And HBase has conditions where normally we always will accept writes also, except when a region server fails, at which time the region needs to be reassigned. And the period that it takes for the region to be reassigned, it does not allow writes. The client will block and retry until the region becomes available again. Okay.
Okay, I think that we can take one more question.
Regarding to the correlation application, you mentioned in the Termico,
yes,
collect the event, right? Do you have any performance data about the correlation jobs?
I do not have that information.
Thank you.
Someone in Termico has it, but I don't.
好，还有没有？还没有？还没有问题 ？Any question? 还没问题 ？Okay.
So you say this biggest change is the Java file, right, for this version? And which part of the HBase code base is most beneficial of this work?
The region server.
Region server?
Mm-hmm. All the I/O path, from RPC to disk and back, all of that was essentially rewritten or re-architected for this release. But it's all in the region server, right? Because in the HBase architecture, the master only mediates with the clients the location of the data, and then the clients talk with the region servers themselves. So all of our I/O improvements have happened in the region server.
But the region server is talk to the HDFS underlying.
That's correct.
And HDFS is implemented in Java.
Yes, it is.
So would that be a bottleneck eventually?
Well, HDFS can be a bottleneck. It's in the Hadoop software stack, right? HDFS sits on the bottom, and then MapReduce is on top, right? And HBase kind of sits on top. We're like a client of HDFS. So any performance limits of HDFS we have as a client of theirs. But I would say that in my experience, a well-provisioned HDFS cluster with reasonable replication settings and performance tunings is not a bottleneck for HBase. It ends up being that the clients are usually bottlenecked, can't write fast enough.
Thank you.
Okay, all right, well, thank you very much.